Hi, good morning, everyone. I'm Ali Rasek, and this is Tuesday, July 9th, 2024. And this is another session of our earthquake engineering course. Yeah, the students are still joining the class, but we have built okay momentum at about 25. 25 is a good number for me. So we can start here. I think I am, yeah, you can hear me and hopefully see me, which is less important. I have shared the screen for you. Basically, we are now, yeah, July 9th, so getting close to the end. And we were supposed to complete the final report by the end of this week. However, the comments were delayed, and so we extended it for a few days until the end of the weekend. Yeah, so Behnam has done a good job, like leaving comments for you guys. And I'm hoping that it's visible. I asked him if it is visible to students. So yeah, write me in the chat or just speak up if you can or cannot see the comments. And they are reasonable. So I think, yeah, if you can see them, start implementing them, and also really try to enhance your submit up for final. We will need very good reports from the teams. So hopefully, no, you are quiet because you agree and you can see the comments. Okay, okay. Thank you for the feedback, Sarah. So I go, let me see, maybe I can do it myself. So I come here. These are the teams. Yeah, I have these teams and say 3 assignments, draft report. So the comments are on the PDF. Can I make it visible to you? Or does anybody know how I can make it visible? The scores are not ready. The grade is not ready because I made a rubric. Oh, press publish. Oh, wait. Publish. I see publish. Publish. Which corner is that? Bottom right. Right of the screen. Oh, yeah. Too visible. Okay, I will do that one by one. So there won't be, as I said, there won't be any mark or grade because I can show this to you. Where is it? Under reports, I have the reports here. Just last night, I created the rubric so that we mark all the reports in a similar manner so that it's fair and people are judged or marked similarly. And so I was late slightly, so marks, maybe we will finish them in a couple of days. But right after this meeting, I will, as you guys said, I will go to the reports one by one and press this publish. Right now, group 1 is published. So then you go to the PDF. Yeah, I will put that there. Yeah, thank you. Like a good question. I will put that. So this is, I don't know which team is this, not your team, Sarah, but anyways, yeah. The comments are embedded in the PDF. And you can apply them. So I don't know, maybe this group doesn't want other teams to see their work yet. at the end they will present and publish when it's final. But yeah, so I will upload the rubric as well, and then I will publish right after the class for all teams. Let's see if I can do it quickly. But supposedly you guys are now listening to the course, so I don't want to distract you. Then you continue your work. Yeah, don't worry too much about deadline. We can still extend it by 1 day or two. So don't worry if by Friday or Monday you see that you need a couple of more days, just email me. I will extend it. Nothing will change, so it doesn't affect the overall schedule. And I change it for everyone if need be, maybe for by 1 day to 16, 1 week from today, so that you have 1 week to update the report. So at least I go to 16, but if you need maybe 17 Wednesday is also okay. So that's what we have in terms of the planning. Now we can jump back onto our non-structural and nothing comments. So I close this for now. Let's see. Yeah, so we went through a couple of case studies. As I mentioned last time, I actually got these case studies from Earthquake for Architects book, because I thought that they have a nice discussion there, high level, good knowledge for structural engineers. I didn't want to just quickly jump into the equations that we like. So just go through those slides again yourself. Those are interesting discussions and a couple of good case studies. And you can generalize it to other probably similar situations that you will encounter. Then we started looking at the equation, and this is a good estimate for the load on the any non-structural member attached to the structure based on elevation. And I try to rationalize it for you. So this is the weight of the member, and this component is like a factor of the spectral response, the maximum spectral acceleration a structure sees or at the ground level. And because it's at the ground level, we should take it up by some amplification factors to the level of interest. IE is the importance factor, the main primary building importance factor. So it's part of assessing the acceleration. And the important factor here is this SP that basically translates or transfers the base acceleration into the acceleration at the elevation of interest, at the elevation of your non-structural member, and it has components. So there is a element factor from certain table of the code. We can quickly look at that. And so that's basically estimate of the stiffness maybe of the component, and AR element or component force amplification factor. How does the component internally, if it's a spring and mass, internally amplify the response? AX is because that component, I keep on calling it component because in my area of work, we attach components to the dam. So there's always discussion about electrical and mechanical components that we attach to the dam apartment. But anything, like it could be, as I said last time, could be my shelf. And so my shelf is sitting like right now at the office. The office furniture are at the 5th floor, and we want to know what is the amplification at the 5th floor, and that's where this height factor comes in. And one of the students, I think Sarah, she emailed me, and the code is not, I cannot say it's super clear on exactly what they mean by HX and HO. But if when I'm using this equation, my interpretation is HO is the total height of the structure, just like rational or engineering judgment, and HX is the height of the furniture or attachment. So right now I'm at the 5th floor. This building probably has 20 floors. So like it's almost 5 out of 20 multiplied by 2. And then, so that results in the amplification factor, which they call height factor. This has a minimum of 1 at the very, very base, like when it's sitting right on the ground and it's moving the same as the ground acceleration, and a maximum of 3, like 1 plus 2, 3, when it's at the roof level, at the ceiling level. So that's the estimate. We can always do modeling, and you saw that in the sub model we can rate the acceleration at certain elevation, at any elevation, at any node. And you may also consider just designing based on the acceleration you are reading at elevation. Besides, you should also, like if you do that, you should also consider other factors such as RP, because it is a reduction factor, element or component response modification factor. That's different than the modification factors we discussed so far, which was the whole structural modification factor caused by ductility or overstrength. RP appears to be more like ductility, like that component, that particular anchorage that you have used to connect the component to your building, how much ductility will it have? And they have a guiding table. So that's about this equation, which has been important for me. We use that in parallel with modeling. Now, yeah, repeating that equation and the modification factor, the whole modifications, SP, what do we call SP? SP is, yeah, they don't have a name for it, but it's like modifies everything. Be careful about the max and mean of SP, so don't estimate, like if SP by equations is calculated to be 5, and you don't need to go more than 4. So there is a ceiling for this value as well. Now back to SP and its components. So CP, AR, we said that AX, there was an equation because it was only a height factor. So the 3 components that you can read from the table for different categories, and is CP, AR, and RP that you can read from here and insert into your equation, depending on whether we can find this table in the MDCC. Yeah, I'm pretty sure that last year I copied everything from the latest 2020, but yeah, just generally make sure that you are using 2020 now that it's legislated in British Columbia. So the category, whether it's architectural or mechanical, you go into the category, and then the subcategory, say for architectural, is it exterior and interior walls, cladding panels, except for in other categories. And then yeah, you can read the factors right here. So yeah, you can find almost anything in here: towers, chimneys, floors, and rods acting as diaphragms. So all sorts of subcategories and subcategories here. Looks like this one is taken to a node. Maybe the node refers to another section of the code. So yes, I'm trying to make the case that you can find all these factors in here, and AX, there was an equation for that. Yeah, so the rest of the table for mechanical equipment and other system components. You can read them from here. Yeah, nothing much to it, so just reading factors. And there are some exceptions in that article for 1818, such as this one. When the mass of a tank plus its contents or mass of flexible or flexibly connected piece of machinery, fixture or equipment is greater than 10% of the mass of the supporting floor, the lateral force should be determined by rational analysis. Basically, I mean, here the whole idea about component or substructure or elements of a structure is that they are considerably lighter than the whole structure or the floor that they are sitting on. So there is no interaction. Like, say, my furniture is much lighter than the floor, so the movement of the floor is not affected much by furniture. It's only one-way interaction. Like the floor causes change in movement of furniture. But it's possible that the furniture is so heavy that it will change the whole reaction of the structure. And by interaction, probably the best we can do if you think the equipment is heavy, say you have an original SAP 2000 model, and you only have included the floor weight. If it's really heavy, if that component is really heavy, then add it to the floor weight. Then it affects the mold shapes of the structure and the response of the structure. And then we can continue from there. Just use the accelerations right at that location. So that's what I mean by rational analysis. Okay. Now, about connections. Connections to the structure of elements and components listed in the table shall be designed to support the component or element for gravity loads. The connections should also act for gravity, shall conform to the requirement of sentence 1 and shall also satisfy these additional requirements. Except as provided in section 17, friction due to gravity loads shall not be considered. RP for non-ductile connections, such as adhesive or power actuated references shall be taken as one. So remember that RP has similar function as R in the main structure, but this is about the ductility of the component. If the ductility of component is 0, then you don't reduce the forces. RP for shallow points installed mechanical adhesive and casting placed anchors shall be 1.5. So another comment about using RP. And post-install mechanical drop-in and adhesive anchors in concrete shall be pre-qualified. So there are rules and regulations about the pre-qualification. I don't know, maybe you call the vendor and ask if they have done tests and they have done pre-qualification, or they have documents that they say they have done those pre-qualifications. So be aware of those. Post-installed mechanical and adhesive anchors in masonry and post-installed mechanical and anchors in structural steel shall be pre-qualified for seismic amplifications by cyclic tension load testing. So again, so you should be aware of that and ask the vendor. Power actuated fasteners shall not be used for cyclic tension load. Connections for non-structural elements or components of category 1, 2, or 3 of table 41818 attached to the side of the building and above the first level above grade shall satisfy the following requirements. So some requirements in this case that should be aware of, you should be browsing through them, but I will read them. And edge ductile connection is one where the body of the connection is capable of dissipating energy through cyclic inelastic behavior. So we already discussed the concept of ductility, and similar concept applies to connections. So it should be almost able to verify a ductile anchor, say a steel anchor with good free length is ductile because it can elongate before it fails. For suspended units, isolated suspended, sorry, isolated suspended equipment and components such as pendant lights may be designed as a pendulum system, provided that adequate chains or cable capable of supporting 2 times the weight of suspended components are provided and deflection requirements are satisfied. So that factor of 2 for pendulum is important. Like you assume you have twice as much weight. Going to the, just I can actually do this one also quickly, the concept of floor design spectra. That's more for the people who want to use the result of analysis and computer model instead of that equations that we showed. So just trying to say we have a design spectra, we have an acceleration design spectra at the base of the building, which is related to the ground. And we should be able to obtain similar design spectra at the higher floors. That's what they call it, floor design spectra in buildings. And sometimes in non-buildings, we keep on using the same terminology, just means a spectral acceleration at a higher elevation. I sometimes think this is a better terminology in a structural design spectra, but then its popular name, more popular name is floor design spectra. Basically, floor design spectra is developed from the response of a structure to the earthquake. What should we do? What are the steps that we take? Perform response history analysis, also known as time history analysis, for a set of earthquake records. So you have your building and you have a set of earthquake records and you run them, or you just measure the response of the building to all those earthquakes, record the response of a structure at the points of interest. So at the points of interest, you record the response, and you develop floor response spectra for the recorded responses. And then we talked about that, or at least schematically, we said how we can use time histories of acceleration and change it to a spectral acceleration, which is basically the maximum responses. And there are codes for that. SAP 2000 also does that for you. And then we go through a procedure that calls combining, which means basically averaging them in most cases, and widen the response spectrum. This is more schematically. So there are steps that are taken for your typical dam in order to get the response at the top of the dam. I said, like, we use that equation, the code given to us, we can use it, but this is not really building. That equation is more suited for buildings or optimized for buildings. But for other structures, it's could be used maybe for checking, for double checking, but nothing more than that. Going through the steps that you get for your other buildings or for even for your high rise. You have your target spectra, and then a seismologist basically translate your target spectra that maybe you got from NVCC to a bunch of earthquake histories at the ground level, called firm ground, but then at the ground level. And maybe they get it from for the firm ground level, and then they change it, they modify it to the real ground level based on the site specific like rating of the rock. So you have these accelerations, you apply it to your model, and then you read the amplified accelerations on top of the dam, and then you do the reverse of this. You change those accelerations to what is called floor design spectra, which is much higher than the input spectra. And then you average them, average the floor response spectra to floor design spectra, which is we give them to, say, gate designer for the design of their gates. Sometimes there are different departments, so like all this is black box for them. So we go through all this, and then everything that we gave them is this floor design spectra for their gate design on top of the dam. So that was the high-level concept I'd like you guys to know. The FDS is used for response spectrum analysis of a component. Say on top of the dam, you have a hoist system or a gate, and the structural engineer in charge of this part, he or she doesn't need to know much about the dam. We try to obtain FDS for them and give FDS to them so that they use, like they start from this point. They receive FDS and they have their structure, and they basically do a response spectrum analysis as if they are not aware of the dam. So selection of equipment for prescribed level of shaking. And say for electrical equipment to work well, they have some limitations. They have an acceptable level of response, and you can compare their acceptable level of response to their real design spectrum and make a decision on whether that equipment is acceptable or not, or maybe you need to use dampers. Then you connect that equipment to your structure to avoid higher responses. So helps in that regard as well. And deciding whether certain components should be seismically isolated, that's almost what I said, seismic isolation or connection to dampers in order to reduce the response at their location. And yeah, I said that we have flow response spectrum and we want to create the FDS. Normally, if we have many earthquakes, we use mean. So normally we do like these earthquakes, we create or ask the geologist to give us like in the latest code, 11 is like a regular number. Previously it was like 7 or 5 or 3, but now we receive, for a lot of times we receive like a set of 11 earthquakes. So 11, if you have an analysis on 11 earthquakes, which is 5 or more, and we want to assess the design, a lot of times like for gates, just average them. I do that a lot, so averaging a bunch of responses into the design spectrum. Just to get rid of this issue. And then after averaging, you have this greenish curve, which is average between a bunch of curves. There is another procedure called widening. And basically, we try to widen every point on the curve, make it more conservative. And the issue, I think the top reason for doing the widening is that maybe because of the modeling errors, etc., we mischaracterize the period of the system, and we want to create some safety. So by widening it, maybe I characterized my period to be here, and then the average is pretty low, while the real period was here. So this solution causes me to really use the response at this location. So just because I estimated my period to be here while it was really here, accounts for that type of mistake or like mischaracterization. Maybe sometimes we are not even aware of certain features of the structure. Okay, all done with this. So in summary, we talked high level about the components and in architectural terms, and the code requirements. And because these days people do more and more analysis, that really want to obtain everything out of analysis, the analysis method in just high level terms. So we have three features like the good understanding, and then the code solution, and the analysis computer modeling solution. Any questions or comments before I proceed to the next module, basically, which is still. Okay. I wait for about 1 minute. Okay, we continue with the still. A still designed for earthquake. So we just finished the most important section on National Building Code of Canada requirements. Now we will try to go through, I think we don't have too many sessions left, but then we go through a steel and concrete and hopefully wood. I don't think I have anything from masonry. But in general, I think steel is, steel is the most important because it's like the poster child of ductility and favorite concepts in earthquake design. So if everybody, and myself, if I fully understand a steel design and how ductility plays a role, etc., then I can generalize it to other materials which are really less ductile, but then we make them more ductile by proper detailing. Steel is ductile by nature. Again, that's a good chance to revisit the idea of ductile design. A structure, seismic force assisting system, or SFRS, is designed to yield to go plastic in ductile design. That's the ultimate goal of ductile design. So in this case, the ductility is provided by some plastic hinges. In this example, it's in the columns, maybe for, say, for bridges, it's inevitable. For buildings, we prefer that the plastic hinges occur in the beams. But that's a mechanism of dissipating energy. A mechanism forms and undergoes plastic deformation, like rotating at the location of plastic hinge. Forces in a structure increase more slowly or not at all. We looked at this curve previously. So in our naive analysis, which is using a linear model of the system, we just basically we will read a deflection and a force. And however, because of the yielding, this structure can never reach this force. It reaches a much lower force and then remains the same. But it doesn't collapse because it's ductile, like it can take more and more deflection. And that's basic for the reduction factors caused by ductility. The ratio of VE and VD is the reduction factor that we are using. However, in most cases, in most periods, the idea is that the deflection that we obtain from a linear analysis would be the same if we do a linear analysis. So when we naively do our SAP 2000 linear model, the deflections are generally considered correct if you are not using reduction factor, and the forces should reduce. But note that the lateral forces we use in SAP are reduced. So you basically, it's the reverse. So you read the correct force and the wrong deflection, and then you should like reversely multiply by the R factors to get the correct deflection. So that's the way practically we do that. We don't apply the full force, we apply the reduced force. And therefore, the forces are correct, the deflections are underestimated. So energy is dissipated, a structure getting closer and closer to damage. And structural components can be designed for smaller forces than would be the case for elastic. Yeah, they can never reach the elastic response. And however, this is only possible if detailing is proper and capacity design check reappears here. So it's very important that the members that are intended to be ductile become ductile and other members don't fail. Otherwise, we get a catastrophic failure because some brittle member will fail first. So like the context is that we are taking in terms of a steel now. A steel seismic design. A steel is highly useful material for seismic applications. It has high strength, high ductility, and ability to design and analyze with high degree of confidence. Steel seismic forces resisting systems are designed to behave in a ductile way, and some configurations can take very heavy loads, meaning lateral loads. But we previously mentioned that, but we will discuss further. Now, as I said, like the steel is like the poster child for ductile behavior of a steel. And so we have the material level behavior of a steel. It's a stress versus a strain that you must be like familiar with. A steel just deforms up to some level where the yielding starts. And then if you keep on pushing, it will yield further and further until like when it has reached like quite large deflection. Another feature kicks in, which is called a strain hardening. Then it becomes slightly stiffer until it fails. So the different parts are elastic range versus inelastic range. And then within inelastic, we have the yield, like flat yield, versus a strain hardening range. If you do cyclic test on a steel, if you say increase the force within the elastic range, it will go back to where you started. when you yield it slightly and then release it, it will have permanent deformation because it will like spring back as if it's elastic, and therefore a permanent deformation remains. It's called residual strain at the strain level or residual deflection. And the ductility, there's a definition for ductility. That's the maximum deformation divided by elastic deformation. That is pretty high in the steel. The behavior of a steel can be shown with a strain plot. We talked about it. The modular elasticity of a steel, that's famously 200 gigapascal. That's the like slope of this line. Yields at location B. Between B and C, residual strain will be created if you unload it. And then between C and D, there will be a strain hardening further than D. And after that, we get close to failure and fracture. Cyclic behavior. The red line shows the elastic behavior, at least up to this point where there is no strain hardening. But if you do cyclic, means load and unload and load and unload, as we said, A, B, C, then we come down to C prime, and then we can go further down, yield again, and go through a circle. And the cyclic behavior causes dissipation of energy. So that's something beneficial to us. That's something that we like to see. However, it happens like this is showing displacement versus force for this bracing system. However, we can take full advantage of this system if we have a proper detailing, meaning proper capacity protection for other members. Otherwise, part of the load pad, which is non-ductile, will break, and you will not see this beneficial behavior, like a connection might break if it's not capacity protected. Common steel sections that are used in seismic force assisting system: I shape or wide W flange, C channel, HSS in different shapes and angle. So you should be familiar with that. Probably you have taken a steel course. And we talked how the behavior is at the material level, now at the section level. How that material behavior causes the behavior at the section. We normally design for for less than yielding. Therefore, the distribution of stress versus height is something like this. Like if you apply this moment, the top flange is in tension and the bottom flange is in compression. And then if we gradually increase the M, the material yields, and therefore the stresses cannot really go beyond Fy. And therefore you see that instead of triangle, full triangle, there's a limit of Fy. And we can imagine the force increases so much that almost this whole length is in tension at yield, and this whole length is in tension in compression. So that's the level that we call plastic moment. And in terms of moment, this section cannot take a higher force, higher moment force, but it can keep on rotating. After that, the force doesn't change, but rotation can increase until there's rupture. If you apply, like forcefully apply force, which is more than MP, it can withstand up to MP, but then it keeps on rotating until it ruptures. So that's a basic idea about plastic hinges. At this point, we can say that the plastic hinge has been created. And as I said, this is easier to explain in steel, but we carry on the same similar concept to concrete. Moment hinge in W section. Again, yeah, we talk about the W because it's symmetric, it's easier to describe, but it happens to the other ones as well. So basically, moment versus rotation. Initially, it's elastic up to this point, and only like a millimeter has reached to my. Then there is the change between my and MP, where the stiffness of the system is gradually reducing because more and more yielding is happening. So from my to MP, we have a reduced stiffness as the structure gradually, or the section is gradually yielding. And after MP, we see no more resistance. Like the structure cannot really take moment larger than MP. So the plastic hinge becomes flat. So practically, it has 3 lines. But I think for practical cases, you can use 2 lines, like the elastic and then fully plastic, just for modeling purpose. Or if your software can take 3 lines, then why not? 2 lines should be also okay. Elastic and then plastic. That's an assumption, good assumption. Yeah, so explaining the same 2 sketches, the same plot was brought in here, and the stiffness reduces, and eventually there is a cap to the moment, and any moment larger than that will cause failure. The more compact section is the idea of the compact sections. Maybe you already saw that in your steel course. The more compact section is the more stable plastic hinge. It basically means more beefy, because if it's too thin, especially the flanges, if they are too thin, they may really buckle in before they reach MP. So before they reach MP, if this is too thin, they will buckle in, therefore they cannot really reach MP. So that's why the code discusses the compactness. And it talks about different classes of compactness. Class 1 can develop the MP, so that's the beefiest one, and sustain cyclic rotation beyond the theta P, even after it reaches theta P. Theta P is the rotation when we have plastic hinge. It can even rotate more, and it will not immediately break. It can sustain really. It has, like, what it means is that it has excellent activity. It can get into the plastic range rotation, and then collapse at a much larger rotation. So class 1 is the ideal for ductile behavior. Class 2 is just reaches MP, but nothing more. After MP, it really buckles and is not usable. Class 3 at least can reach MY, which is at least can work and get to borderline yielding. Class 4 cannot even reach there, and it will buckle even before the moment reaches that level. So we should be aware of these classes. So seismic force assisting systems within the context of steel. Canadian Steel Design Code. We get into that in the next session. However, this is it is almost the same between different codes. There are recognized as 10 different seismic force resisting systems. I don't know all of them, but these 5 are the important one. The concentrically braced frames, we introduced them. Buckling restrained brace frames, I will show that to you. Eccentrically, we briefly mentioned them. Moment resisting frames and shear walls, which means steel shear walls. Concentrically braced frames, meaning that the 2 braces are meeting each other. CBF, let's call it CBF. CBFs are vertical cantilever trusses that resist seismic load through axial tension and compression in braces. So one brace is in tension and yields, the other one is in compression and it may buckle, except if we prevent it. It is the simplest system and has a high lateral strength and stiffness. Energy dissipation is done through inelastic deformation. Both yielding and buckling will dissipate energy. However, note that the buckling, although it dissipates energy, but it's like out of control, like it might buckle in any direction. So we don't really like this buckling. We prefer to prevent it or not be dependent on it. Tensile yielding and flexural hinging due to buckling in compression. So when this buckles, parts of it becomes in tension or compression, mostly in compression, and there might even be plastic hinges because it bends a lot when it buckles, and those mechanisms dissipate energy. Typical test on the shaking table on concentrically braced frames, just showing a good nature in terms of dissipating energy and yielding. And looks like somebody has used the program Drain 2D and has compared with experiment. They are on the same line, comparable, good match. So the behavior, like in Drain 2DX, they account for the yielding, tension, and plastic hinges. Looks like that those phenomena explains the behavior well. So the phenomena that we discussed, the yielding in tension, plastic hinging in compression, has been good enough to explain the behavior because Drain 2DX and experiment, they match well. Example, concentrically braced frames, where the 2 frames meet each other. Say here at the floor level, they meet each other. They might also just cross each other. This one appears to be crossing each other, but it's a lot more than 1 floor. So it's like each of these crosses are multiple floors, maybe, I don't know, 6, 7 floors, as I can just estimate. Even this one could be more than 1 floor. So it's not exactly correlated with flooring system. Although in a lot of buildings, typical buildings that we design, it's like 1 bracing bed per floor. As I said, the buckling, the tensile side of yielding or dissipation of energy, we like it really because well behaved in a way. The compression side, which means buckling and in a way creating the plastic hinges, it appears to be out of control. So definitely it's not favorite. And there's this idea to prevent buckling. So in this system, there is like using maybe in a concrete or maybe a steel, try to cover the bracing so that they don't buckle out and they only yield in tension and compression. And yielding in tension and compression is a phenomenon where the energy is dissipated. So the bracing members are restrained using tubes. Those tubes could be concrete. Often bracing members are procured from a vendor. So there's a vendor that they are not really constructed in place because it's difficult to analyze and design to prevent buckling. A vendor has done that, and they basically sell the pre-tested, and it should be tested as well. Sometimes analysis is not good enough, so they do the test. They make sure that no buckling happens with that sleeve. Bracing members yield in tension and compression instead of buckling and compression. This leads to better energy dissipation, accommodate larger inelastic deformation, and these structures are considered more ductile. Another showing of the section of a typical buckling restraint brace. As I said, there is a sleeve. Like this sleeve is now a combination of a steel tube and concrete inside. However, this core is really the bracing that you are designing for. The steel tube is not part of the, or maybe it is, but in most cases I don't assume that the steel tube is part of the lateral force resisting system. The core is definitely, and using the steel tube and concrete sleeve, we try to prevent buckling. So that's the way it's made. And yeah, so here it shows that like BRBS, which is the buckling restraint brace, BRBs, they act nicer, like both in tension and compression in both directions, while the ones that are like this is a typical result for this setup. It acts well if it's not restrained. It acts well if it's traditional. It acts well in tension. In compression, it suddenly buckles and behaves poorly. And then in tension, it behaves okay. While the blue line, which is buckling restraint brace, it acts well in both directions and dissipates a lot more energy. So that's the idea behind it. Buckling restraint brace frames used in real building. I don't know their location, but obviously there's a concrete sleeve that is preventing the buckling. Eccentrically braced frame. These are, there are success stories that they were innovated more recently, comparingly more recently. And what we do in this design is that the two braces are really, they don't meet each other, they are eccentric, and like part of the beam is actually between the ends of the braces. And that part of the beam is the main energy dissipation strategy in the eccentrically braced frame. It yields in shear, so it's called shear link. Sometimes we call it shear link. And that yielding helps with dissipating a lot of energy, and it's under control, and it's limited. It's very limited. Like in this area, in a severe earthquake, you could have yielding in this area, and you have the potential to only repair this area. So the bracing members do not meet at the same point. The link beam or shear link beam is designed to yield and anticipate energy. Yielding can either occur as shear in web or in flexure at the link between ends. So it could be shear, mostly it's shear, but it can be bending as well. Can be a chevron or single brace with yielding between the braces and column. So these are chevron type, but what it says here is that you can have only single brace going almost all the way to this joint, but with a slight offset. So that's another configuration. And everything else, again, is capacity design. Like even now, right now, with this design, we are not even dependent on yielding of braces. So everything is capacity design, including the braces. We only want this shear link or moment link to yield, anticipate energy. And yeah, so there have been a lot of tests in the past couple of or 2 decades to verify them, that they behave well, and there are recommendations on how to detail them. Like you see, these plates that are welded to them are shown here as well. So they could be part of a typical design, or maybe they are even provided by a vendor. That you just connect this link between these 2 points, and supposedly after the earthquake, we can even remove it and replace it, get a new one and put in there if a severe earthquake happens. So they are well behaved. And yeah, so there's a link here by Dr. Bruno, who is very famous, but you can read through this link. He has done a lot of tests. I think he's in New York University or something like that, in Buffalo, so he's quite famous. Using eccentrically braced frames in the real case, so yeah, these are like eccentrically braced frames. The 2 braces don't meet each other. There is a link in between. The energy is dissipated mostly through shear. Moment resisting frames, we previously discussed it, where beams and columns are rigidly connected so that they can transfer moments, and that will cause plastic hinges to happen in beams and columns. We prefer, in buildings, we prefer most of plastic hinges to be in the beams, so that at least you can easily, or more easily, replace them if needed. Replacing a column is a lot more difficult. You can at least look at it that way. Besides the fact that column is the main gravity load carrying system, and yielding of column endangers the stability of the whole structure. So we prefer the plastic hinges to happen in the beams. Moment frames are very common due to ability to have clear space. Also, your architect will also like it because a lot of room for opening. There's no bracing or shear wall to prevent openings. Lateral resistance is provided by full moment resisting connections at each level. So moment resisting connections at each connection between beams and columns. Energy dissipation is achieved by yielding at the member ends. Normally, the maximum moments during earthquake for the side load is at the ends. So typically, if you do a few try and error, you will see that for lateral load, earthquake or wind, the maximum bending is at the ends. For vertical load on beams, the maximum is in the middle. But like plastic engines is recommended for mostly for earthquakes, so we depend on them at the end. Preferred scheme is to have yielding in the beams. In multi-story buildings, column hinging may lead to soft story instability. Yeah, so we don't want soft story and we don't want instability. Additional hinging is typically designed to occur at the base of the column. Yeah, sometimes you will see that having plastic hinges at the very base is inevitable. We cannot do much about it. Other than that, we don't like to have them through the length of the column. Again, modeling that you guys might also like to do later on as a job or as research, just testing the behavior of the moment connections. As you see, this panel is very important. It is red, so there's a lot of a lot of shear actually happens in this panel. It's again sort of shear panel, and therefore it should be designed properly. Like there are stiffeners at the ends of it, or maybe sometimes even in the middle, to avoid buckling in this plate. In this other case, the highest stresses are in the flanges. That's exactly where we want them. We want them to be in the flanges, and that indicates that the plastic hinging is happening right here and here. Yeah, and there have been many, I don't know, I said millions or thousands, definitely, of testing being done around the world, because in some earthquakes, the moment connections were behaving poorly, and therefore there was this reason, there was this, I mean, the people in the research, they had all sorts of reasons to test it a lot to make sure which configurations are better. Therefore, it's recommended to use correct configurations that accounts for like the shear zone here is probably properly restrained, etc. So that our final intention is this picture. Like we want the plastic hinge exactly, and yielding happens exactly where we want it to be at this location of that is intended for plastic hinging, and we don't want unwanted yielding in other locations. So yeah, so there are like examples and even guidebooks, etc., with a lot of approved connections that are tested and pre-tested and pre-qualified, especially for state-of-the-art. They have been good testing system, and we know which ones are verified. Shear walls, it's like using a steel shear wall. Yeah, for very tall building, I don't know. Yeah, I haven't seen, or maybe I didn't pay attention to buildings that where the only resisting system is a steel shear wall, but theoretically, it's doable, and you can have a steel plates all the way through the height so that they act as shear walls. Lateral resistance is provided by a steel plate welded into a frame. Energy dissipation is achieved by yielding and buckling of plates, which is okay. Tall multi-story shear walls will behave like a flexural cantilever. So that whole system is like a flexural. After you add the shear wall, they act like a flexural cantilever. They are often coupled with a frame, resulting in hybrid response. Shear mode deformation in rigid frame, fractal mode deformation in shear wall. So shear wall, normally it has a shear behavior, not a bending behavior. While in like moment resisting, you will have more like a bending type of behavior. when you have the combination of the two, both systems are active and there is an interaction in frame and shear wall. And the shear wall acts more in shear, building acts more like in, or dissipates energy, or responses more in bending. And when the two are connected to each other, there is an interaction between the two. So it's halfway shear, halfway bending in a way. Yeah, similar to other cases that have been testing, and the behavior is verified. As you see, it's like shear versus deflection appears to be good shape and symmetric and acts well in both directions, and it's dissipating energy. So that's what you want to see in your energy dissipating system and shear wall. Ductility factors, we read them from National Building Code of Canada. I think we looked at them once. Generally, these are for steel. So as you see, for a ductile moment resisting frame, you can have the ductility reduction factor of as high as 5. And if it's not defined above, it's like 1. So if the structure is not ductile, the ductility factor is only 1. But the higher ones, the higher values go to the ductile moment resisting frames and to the ductile plate walls that are very good. And then there are some other values which are like moderately ductile. We will define that. Limited ductility, we will define it. And yeah, so ductile plate walls, they show very good ductility. Conventional construction, even if there is not much supervision, but it's a moment, there is supervision, but there is not enforcing of these details. Still, we can get a ductility factor of 1.5. A reduction factor caused by ductility, which is 1.5. Yeah, so that was first part of steel. Let me know if there are questions. Otherwise, I try to just open the next one. Yeah, that's diving into the code. That's what we intend to do in the next session on Friday. Dive into the code for steel design, which is CSA S16. One of the latest ones was published in 2019. And their class number 27 focuses on the earthquake design for steel. That's the code. Let me close this. So this is the typical code if printed. And sometimes, or most of the time, it's accompanied by hand-cut steel construction, which is a very good tool with lots of nice tables. You don't need to do calculations. You can read the values from the table. And in CSA S16, class 27 is focused on a seismic design. Generally, it's based on limited state design. I think in Canada, we call it limited state design. More internationally, it's famous as LRFD, load and resistance factor design. So we can browse through class number 27, and it describes different types, different levels of ductilities we can achieve by different configurations, and with some explanations on how to achieve that configuration, all the way from what they call type D ductile moment resisting, where the reduction factor caused by ductility is 5, and then moderately ductile, where the factor is only 3.5, and limited ductility, where the reduction factor is only 2. Note that when we have limited ductility, the reduction factor caused by overstrength also reduces from 1.5 to 1.3. So basically, depending on how much effort you want to put in and how much detailing you want to go through, you can achieve different reduction factor. Like total reduction factor is, in this case, is like 1.5, which is 7.5. In this case, it's only 2.6, which is about 1/3. So this structure, like it's less detailed, but the force that goes into it, if it's like sometimes called even privates using it in certain seismic categories, but if the code allows it, the force would be 3 times as much. The reduction factor is only 2.6, where here we have a reduction factor of 7.5. So this is the moment resisting, concentric, eccentric. As you see, eccentric, the code likes it better than concentric. And buckling restraint also, the code sees some benefit in that. Using plates, again, ductile, moderate, or limited. And conventional, only 1.5. That's what next time we'll go through the case study, like 1 or 2 of these items, so that you just get a sense of what the code requires in terms of capacity protection, etc. So we have 1 more minute. Let me know if you have questions. And other than that, have a good rest of the week. Focus on your report, improve it really well. I will publish all the comments, and then we will provide marking very soon. Right? Yeah, thanks a lot. See you on Friday.